In the last lecture, I discussed about the classification of definitions as well as classification of polymer blends with some examples. Now, let us little discuss on the miscibility aspect of miscibility criteria of the component polymers to form a successful blend. Now, miscible blends can be say miscible one phase system, it can be partially miscible system or immiscible two phase system. So, partially immiscible two phase system or immiscible two phase system. Now, when these two components are mixed, we must consider this thermodynamic parameter, this delta G, the free energy of mixing. When the two component polymers are mixed, this delta G or Gibbs free energy of mixing should be negative. Now, in that case, we must consider this equation, the famous equation delta G is equal to delta H minus T delta S minus T delta S, where it is the free energy of mixing, the enthalpy change, and this is the entropy of mixing. This is heat of mixing and this entropy of mixing, and T is the absolute temperature. Now, here delta S is essentially negligible. Why? Because the component polymers are having P1 and P2 are having very high molecular weight. Now, if we compare the miscible solution of this P2 with in P1, say P2 may be solute, P1 may be the solvent, and in this system both the components P2 and P1 are of very high molecular weight. If we compare this system with a simple solution of say sugar in water, when you put sugar in water, this sugar dissolves in water and we get a uniform solution. Solution of sugar in water. Now, this sugar molecule is very the size of the sugar molecule is very small and size of the water molecule is also very small. Since these two smaller units are mixed together having their closed solubility parameter, they are miscible and they enter into solution and form a uniform distribution of sugar molecules in water phase. So, if we go details, we can explain this phenomena of solubility, solution or dissolution phenomena with the help of liquid lattice model we can understand. Now, the picture is little different in case of polymer. Here the in case of your simple solution, the entropy of mixing of the sugar and water is quite high because of their discrete molecular nature. Here the entropy of these polymers will be very less, almost negligible because of the high molecular nature. Now, a particular segment, suppose this is a polymer chain, a small segment may be little mobile, but the mobility of the polymer molecule as a whole is not possible. Say for example, this P2, mobility of P2 in P1 is not feasible that way. So, the entropy of mixing of P1 and P2 is negligible. Hence, the delta H must be, this delta H must be negative or 0 in order to make delta G negative. So, delta H is very small. So, in order to make this delta G negative, the delta H must be made very small or 0 or negative or 0 for the formation of miscible blends. Now, requirement for a negative delta H value can be met when there is a physical interaction or physical attraction between the component polymers, suppose hydrogen bonding. Now, are various models of this to explain the immiscibility or miscibility of the component polymers, and this immiscibility is a consequence of very small combinatorial entropy change when two high molecular weight polymers are mixed. Now, if we use this Flory-Huygens lattice model in order to obtain this entropy of mixing delta S for a blend of two polymers P1 and P2, we can use this equation delta S equal to RV by VR into phi 1 by x 1 ln into ln phi 1 plus phi 2 by x 2 into ln phi 2, where R is ideal gas constant, V is the volume of the total volume of the blend of the component polymers P1 and P2, and VR is a reference volume of the smallest repeat unit of the two component polymers, or the molar volume of the smallest repeat unit of the two component polymers, and phi I or phi 1 or phi 2 are the volume fractions of the two component polymers. Phi 1 is the volume fraction of P1, phi 2 is the volume fraction of P2, and x 1 or x 2 are the degree of polymerization dP, that which is related to molecular weight. dP is related to the molecular weight of the polymer. dP into n, that means degree of polymerization, if it is multiplied by the number of Mar units, then we can get the molecular weight of one of the Mar unit into dP, weight of the monomer unit into dP, degree of polymerization, we get the molecular weight of the polymer. So, in that case, this x 1 is the degree of polymerization of the component polymer, and x 2 is the degree of polymerization of the component polymer 2, and they represent their corresponding molecular weights. So, we can utilize this model in order to calculate this entropy of mixing of the two component polymers, and the Gibbs free energy of mixing is given by this relation delta G is equal to RT V by VR into phi 1 by x 1 ln phi 1 plus phi 2 by x 2 ln phi 2 plus an interaction parameter has been introduced in the third term, chi 1 2 interaction between the component polymer 1 and the component polymer 2. There is the volume fraction of the product of volume fraction of the two polymers phi 1 and phi 2. This interaction parameter is nothing but the interaction of one polymer molecule with the another polymer molecule in the blend. Interaction can be of different nature or a sum of different types of interactions between the two component polymers, that can be through some chemical reaction of the two functional groups of the two different polymers, or there can be hydrogen bonding, there can be entanglement between the segments of the two polymer chains, or there can be van der Waals interactions or secondary interactions arising out of the London dispersion force. So, this interaction parameter, which is again related to the solubility parameter of the two component polymers, this is very much important, and with the help of these parameters one can calculate the Gibbs free energy of mixings. Since the degree of polymerization x 1 and x 2 of two component polymers appear in the denominator, the right hand side of the equation of entropy of mixing, this means this one, entropy of mixing will be of high molecular weight polymers is very large, and therefore, the delta S is very small. So, that means this x 1 and x 2 comes in the denominator. So, the delta S delta S component becomes very small. So, in order to get delta G to be negative as a necessary condition of miscibility, then there is no other option but to have this delta G negative or 0, this delta G to be negative or 0 or very small positive value. If even if it is positive, that should be very small. So, this term becomes bigger. So, ultimately it becomes negative and delta G will become negative. So, miscibility requires favorable interactions between the two polymer blends. So, that is actually known from this equation where this interaction parameter is included. Let us look into, after having this miscibility criteria, let us see the successful polymer blends, say polymer blend of polymer 1 with polymer 2. Say if the polymer 1 is polystyrene, then what could be the second component polymers? That can be, say one example can be poly 2,6-dimethyl 1,4-phenylene oxide. So, polystyrene with this polymer can have a good blend. Polystyrene with polymethyl vinyl ether can be a different blend, new blend of polymers or polymer blend. Polystyrene with tetramethyl bisphenol A polycarbonate will be again a new polymer blend. If we want to develop some fire retardancy or polarity etc. in a polymer blend, in a polymer product, we can take polyvinyl chloride as one of the components. Now, we can mix polyvinyl chloride PVC with polycaprolactone, that is a biological polymer or that is your biodegradable polymer. So, we can mix polyvinyl chloride with polycarbonate, or we can take the PVC as the matrix, in which we can include little amount of polycaprolactone. Then we can mix, we can have a blend of poly PVC with nitrile rubber. Now, PVC nitrile rubber blend is a very successful blend for electrical insulation, electric cables. Nitrile rubber PVC blend. So, nitrile PVC blend very good for electric cable application, electric cable. For heavy duty electric cable, for high voltage electric cable, underground high voltage electric cable, this after polyethylene insulation, this nitrile PVC blend is used as a sheathing material, or PVC is used to coat conductors for domestic wiring. Then polyvinylidene fluoride is a fluorinated polymer that can also be blended with polyethyl methacrylate, or that can be blended with polymethyl methacrylate. Now, these their blending capability, their miscibility etc. can be understood if their chemical structures are written. If they are looking into their chemical structure, one can understand their miscibility of these component polymers mentioned in this table. Now, let us look into different types of blends and methods of their preparation. Say there can be a type of blend known as mechanical blend. Such mechanical blend are obtained by mixing of the polymers at temperatures above glass transition if the component polymers are amorphous. If the two component polymers are amorphous, so those two component polymers can be mechanically mixed in mechanical blenders, say like polymer mixer, say 2-roll mixer or an internal mixer, by heating the polymer above their glass transition. Above their glass transition, the polymer will become soft and flexible, and then those two component polymers can be amorphous component polymers can be mixed. Now, if the polymers are semi-crystalline in nature, then the polymers are to be further heated to higher temperature beyond Tg, near to their melting temperature or softening temperature. At that softening temperature, the component polymers, semi-crystalline component polymers can mix easily and it form a blend, that is known as mechanical blending. Now, mechanochemical blending or mechanochemical blend, that is another class of polymer blend which is prepared by simultaneous application of mechanical shearing as well as some chemical reaction. So, mechanical shearing and chemical reaction both help mixing of the component polymers, and they are mixed at high shear rate. It is two component polymers are stirred at a very high shear rate, and the polymers degrade during such shearing, mechanical shearing, and generate due to the cleavage of pyrolysis of chemical bonds that forms free radicals. Those free radicals form complex mixtures of different ingredients developed or produced from the component polymers, and that can form block or graft component also. So, this way by mechanically two polymer components are mixed, and during such mixing at high shear rate, what happens? Chemical bonds are broken, that means the polymer molecules are degraded. During such degradation, during the breaking of the polymer chemical bonds, free radicals are created. Those free radicals interact with each other to form a new product, and that can be a kind of graft polymer produced by mechanochemical mixing blending, or that can be a complex mixture of a block copolymer and a graft copolymer, graft components. So, I should not say copolymer, block or graft components. Then solution cast blending. Now, sometimes there are certain polymers which are really difficult to dissolve in some solvents. In that case, we can go for mechanochemical blending, or mechanical blending by mechanical shearing. Now, there are certain polymers which can be dissolved in some suitable solvents. Solvents are available. In those cases, the solvents are selected or proper with the after proper selection of proper solvent composition, the component polymers are dissolved in a common solvent and they are mixed, and after mixing the solvent is removed by evaporation, and that can be collected, recovered for reuse, and the product is becomes a blend of two component polymers. So, in some cases we can use some solvents for solution blending. If it is not allowed, then we can go for mechanical blending or mechanochemical blending. Now, there are certain problems with these solution class blends, because this cannot be an environmental friendly technique. Now, basically these are organic solvents. Now, these organic basically these are organic solvents. These organic solvents are not environmental friendly. This leads to different hazards, health hazards. So, it is better to avoid use of organic solvents, but in case of some specialty applications, special cases, this solution cast blending technique can be followed. then latex blends. Now, there are certain polymers which are synthesized by emulsion polymerization technique. Now, emulsion polymerization leads to form a polymer latex. Ultimately, the polymer is obtained in the latex form. That means, polymer molecules are dispersed in a dispersion medium with which are stabilized by emulsifier molecules. So, that is known as polymer latex. Now, this polymer latex can be used directly to make some product, or the polymer is coagulated for isolation from the emulsion or from the latex to obtain a dry polymer. Now, this is a case of synthetic polymer latex. That means, polymer produced by emulsion polymerization technique in artificially. Now, there are some naturally occurring latex, say natural rubber latex produced by Hevea brasiliensis tree, that is also a latex known as NR latex. Okay. So, we can have polymer emulsions or polymer latex. Either we can isolate the polymer from the latex to get dry polymer, and you have seen mixing or blending of dry polymers involve huge machineries that needs huge energy consumption as well as involvement of high energy shear mixing. We can avoid that if we go for latex blending. That means, blending at the latex stage. That means, we can have a P1 latex, we can mix this P1 latex with the P2 latex, emulsion of P1 polymer can be mixed with emulsion of P2 polymer. Then after mixing in the latex stage, then we can have a blend of P1 and P2 latex. Then we can go for coagulation. We can coagulate this blend, latex blend. We can have a dry blend of P1 and P2 polymer. Then next is interpenetrating polymer network, IPN. This is a case where a different monomer is polymerized and cross-linked in a Solent cross-linked polymer. So, we can have a polymer 1 which is already cross-linked, then that is put in a solvent or in a liquid phase of liquid phase of monomer of the second polymer, which will swell the first cross-linked polymer. So, we take a cross-linked polymer, say polymer P2 or polymer P1, any of the two polymer in cross-linked stage, we place it in the monomer of the second polymer, which will swell this cross-linked polymer. Then after swelling of this cross-linked polymer by the monomer of the second polymer, this monomer will be polymerized. So, this polymer of this monomer, the polymer of this monomer will be grown inside the cross-linked network of the first polymer. So, this way the product which is formed, that is known as interpenetrating polymer network. there can be a semi interpenetrating network, or we can say a pseudo interpenetrating network polymer. In this case, we have to consider a different kind of monomer whose functionality is more than 2, that is polyfunctional monomer. So, for example, glycerol. Glycerol is a trifunctional monomer. Or pentaerythritol, penta, known as pentaerythritol, containing 4 hydroxyl group. So, such type of functional polyfunctional, or we can take phenol, that is a trifunctional monomer. So, this way we can use polyfunctional monomer which can be polymerized in a second thermoplastic polymer matrix. So, thermoplastic polymer matrix will constitute one network of one polymer, in which a second monomer having more than 2 functional groups is polymerized, and that will lead to again a 3-dimensional network system within the thermoplastic matrix. So, that is known as semi-IPN. Since it is thermoplastic, it is not cross-linked, whereas this polyfunctional monomer having functionality more than 2, that will form a 3-dimensional cross-linked network. So, this is cross-linked, this is not cross-linked. So, we call it a semi-IPN network or pseudo-IPN network polymer, network blend. Simultaneous interpenetrating polymer networks. So, different monomers are mixed together, then they are homopolymerized and cross-linked simultaneously. That leads to simultaneous interpenetrating network system. Then interpenetrating elastomeric networks, IEN. In that case, latex polyblend, as I just described few minutes back, that latex polyblend, if it is cross-linked after coagulation, here this it is coagulated, latex blend is coagulated. Now, during coagulation we can mix some cross-linker along with the coagulants, coagulating agent. So, we have to add coagulating agent and along with the coagulating agent we must add some cross-linking agent. Which will remain dormant, remain passive during coagulation stage. After coagulation of the 2 component polymers along with this cross-linking agent, it is washed and purified, then it is given a shape and heated in an oven or in a mold, where during heating this cross-linking agent present in this coagulated polymer blend will decompose to form some active ingredients which will form a 3-dimensional network of the polymer chain. That means, that will lead to a cross-linked polymer morphology. So, that kind of system is known as latex interpenetrating elastomeric network, and it is done from the latex stage itself. Let us look into the different types of equipment necessary in order to make this polymer alloys and blades. Now, this can be such mixing equipment can be of batch type or continuous type. Roll mills, say open roll mills, the cross section of open roll mills look like this. The cross section view of one roll, the cross sectional view of the other roll. Okay. The gap between these two rolls is known as nip gap. Now, this polymer actually raw polymeric material component polymers are placed over the roll surface and these two rolls rotate in opposite direction. Not only that, in order to get this shearing action between this gap nip gap within the nip gap, the two rolls rotate in differential RPM. That means, RPM of the first roll can be, if it can be say suppose 18, the RPM of the other roll can be suppose 15. So, what happens? The stationary roll, so the first roll this roll rotates at higher speed than this roll. So, at any instant of time one roll appears to be stationary to the other roll, that provides the shearing action over here, and that shear action breaks down the molecular chains of the polymers, or that generates heat and it makes the polymer soft, decreases the viscosity. So, by this principle we get a mixing of these component polymers in a two roll mill, and internal mixture is a variation of this open mill. The cross sectional view of this internal mixture again, that is basically enclosed in a chamber, and here also the design of the roll is not circular, evenly circular here, but it is not circular, that can be of different design, that can be of this design, not like this cam type, it can be of cam type design, rotor design is different, that can be actually modified depending on the necessity of amount of shear necessary over here. Here we can get the shear action at the between the gap at the gap of between the two rolls rotors, as well as this is the wall, stationary wall of the chamber, where we can have also shearing action. Now, there is some so the polymer can be inserted through this hopper, and there can be a ram which can move, this ram can be moved up and down this way to carry this material from the hopper into this zone. So, this way we get this we can have a facility of polymer mixing in a closed chamber, and there can be a dumping door at the bottom. So, after mixing, the mixed product can be dumped down from here. So, that is known as internal mixture. So, there are various type of internal mixture, say Banbury mixture, or there can be many other names. So, internal mixture or kinetic mixers. So, these are all batch mixers, that means after mixing of one batch, again the second batch is to be loaded, then it gets helps in mixing. So, through shear action we get this mixing in this batch mixer. Then we can have a continuous mixer. Now, continuous mixers are well known, these are actually basically screw extruders having a single screw or a double screw, twin screw, and basically this extruder looks like this. So, this is a screw and this is known as the barrel. This barrel is having some heating zones provided with heaters, having different heating zones. So, material is actually inserted from the hopper into the extruder and the screw flights are there. So, this is rotated by a motor. So, motor rotates the screw and this gives enough shear action between the barrel of the extruder and between the barrel and the screw of the extruder, and ultimately this polymer is carried and there is some heating provision, all these things. So, it decreases the viscosity and gives efficient mixing or blending of the component polymers, and then ultimately it comes out of the die. This is also a technique for manufacturing say pipes, tubes or coating of wires, etc. Also it is used for blending of the component polymers. So, this extruder can be a single screw extruder or there can be a twin screw extruder within the same barrel. So, twin screw extruder is a kind of modification of the open two roll mill. So, it is a modification of again internal mixture in a continuous way. So, continuously polymer is fed to the extruder through the hopper and continuously this polymer after mixing it comes out and it can be chopped to form mixed polymer granules. So, in the form of granules or tablets or rods we can have the blended polymer. Then this can be further used for the subsequent processes to make different types of products. Say it can be used for injection molding of products, or it can be used for extrusion of pipes or tubes or insulation and covering of the electrical conductors, all these things. So, we can have different types of screw extruders, single screw extruder, twin screw extruders, single shaft intensive mixer, twin shaft continuous intensive mixer, disc extruders, motionless mixers, others. Since there is no scope of discussion in details of these different types of batch mixer or continuous mixers, just a mention is sufficient about the different types of mixers available for making the polymer blends. Then let us look into the properties of polymer blends which are developed after mixing. Say we want to improve the impact strength, that means we want to modify the impact strength of a polymer. What to be done? Say suppose we have a PVC, it is having some impact property, polypropylene or polyethylene, these are all homopolymers. So, we want to modify the impact property of these homopolymers separately. These are all examples placed together in one shown in one place over here. So, if we want to modify the properties of PVC, so we can make a blend of PVC with any of these polymers depending of the impact property which is needed. One good example can be said, say polystyrene. Polystyrene is a brittle polymer. Polystyrene is a brittle polymer. To improve the impact properties of polystyrene, if we can make a blend of polystyrene with a little bit of polybutadiene, say polystyrene is a brittle polymer, that means a low impact polymer. To this low impact polymer, if we mix polybutadiene rubber little bit, say 10% or 20% or 30% of polybutadiene rubber with polystyrene, we can get high impact polystyrene. So, high impact polystyrene grade basically it is made by blending of a little portion of polybutadiene or other elastomer with polystyrene, we get a blend having improved impact strength. So, if we take this table as guideline, so this PVC, PP, PE, PC, polyamide, polyphenol ether or thermoplastic elastomers, all these things, these can be used for making a polymer blend having higher impact strength, and these are considered as modifying polymer: ABS, SBS, EPR, EPDM, polybutadiene, styrene acrylonitrile, etc., polyolefin, high impact polystyrene. So, these can be used for blending with these any of these matrix resins to have newer products. Heat deflection temperature or stiffness. Now, this heat deflection temperature can be, that means it should remain dimensionally stable at elevated temperature or in thermal environment. To increase that heat deflection temperature means it should not deflect within the during surface. So, what is the heat deflection temperature for one particular application means that the polymer should maintain its dimension at that elevated temperature. So, that heat deflection temperature of a polymer can be changed or improved or can be decreased by considering the blend of these matrix resin with these modifying polymers. Stiffness can also be increased. Say these are the matrix resin matrix polymers: polycarbonate, polyamide, acrylonitrile butyl styrene, styrene acrylonitrile. So, thermoplastic elastomers can be used, polyethyramide can be used, polyphenol ether can be used, polycarbonate again can be used with another polycarbonate with PVC or PC, polycarbonate with ABS or PC with thermoplastic elastomer, etc., etc. Fire retardancy can also be improved in one polymer which is not fire retardant or which is not resistant to flame, etc. So, ABS, acrylonitrile butadiene styrene, acrylics, polyamide, polycarbonate, their fire retardancy is not good. So, in order to make them resistant to fire or fire proof or improved fire retardancy, then one can mix ABS with PVC, or one can mix ABS with chlorinated polyethylene, or one can mix say ABS with aromatic polyamide, etc., or polysulfone or copolysiloxanes or polyphosphagenes. So, these polymers are used as an additive to improve the fire retardance property in this matrix resin, either of these matrix resins. So, when these polymers are used as additive, that they are used in little higher concentration. So, it is better to tell them as modifying polymer instead of additive. Chemical and solvent resistance. Now, this chemical resistance or solvent resistance in one polymer can be improved by blending, say polycarbonate, polyamide, polyphenol ethers. So, their solvent resistance can be changed by mixing with thermoplastic elastomers. Okay. Barrier properties, say polyolefins, barrier properties of polyolefins like say polyethylene or polypropylene can be changed by mixing with polyamides, nylons or polyesters or ethylene vinyl alcohol or polyphenylene chloride, Say for example, in case of say flexible packaging of liquid products like say milk and oil. So, those flexible packaging pouches where this milk is packed or oil is packed. Now, that film should be mechanically strong enough as well as that film must have good barrier properties. That is why such type of milk packaging film or oil packaging film, those are basically known as laminated films. Those laminated films are made of basically a blend of LDPE and LLDPE. Now, this is this LDP LLDP blend is used as the outer layers. Within this two outer layer, there is a third film, either this third film is either polyethylene terephthalate or nylon 6. So, this helps in developing the barrier properties in between this LDP LLDP blend. So, this is a laminated film, basically this milk pouch or oil pouch. These are laminated films, where the outer layer is made of LDP LLDP blend and the inner layer is known as the barrier layer, is known as the polyethylene terephthalate and nylon 6. So, barrier properties are developed in this fashion. Okay. Then processability. In order to improve the processability, it is not so easy that all polymers are that way possible processable. So, for example, say polybutadiene rubber. The processability of polybutadiene rubber is not good, whereas the processability of natural rubber is very good. Processability of SBR is also very good. So, processability I mean the compounding of this polymer as well as shaping and fabrication of the compounded polybutadiene rubber with some other additives, that is not good. So, in order to improve the processability, we can use little amount of natural rubber or SBR with this polybutadiene rubber. Similarly, processability of other thermoplastics, polyolefins or other polymers, say condensation polymers. Now, their rheological properties, that means their flow behavior during compounding as well as fabrication, that can be altered or modified by mixing with some other polymers. I mean, say it becomes very difficult to mechanically mix two component polymers due to their very high viscosity or their degradability. Then a second polymer can help to develop good processability, that means viscosity or flow characteristics during extrusion or injection molding or film blowing, etc. So, here say processability of polyphenylene oxide can be improved if some quantity of styrenic polymer can be blended with polyphenylene oxide. Similarly, polyethylene terephthalate, polyamide, polycarbonate, their processability is modified or improved by use of small quantity of polyethylene or polybutadiene rubber or ethylene vinyl alcohol, etc. Then PVC with fluorinated polyethylene, acrylics, polysulfones with polyamide, okay, polyolefins with PTFE and other polymers. Then the properties of the polyblends. The properties of polyblends depend on the extent of phase separation, as I was discussing about the phase separation aspect, nature of the matrix phase, nature of the dispersed phase, interaction between the component polymers. So, these 4 different issues are very much important in order to have optimum properties level as well as broad spectrum of the properties. There should not be separation into different phases, and matrix nature of the matrix phase should be such that they become interactive. So, interface addition between the component polymers should be good, and we must look into the nature of the dispersed phase so that it becomes miscible with the matrix phase, then interaction between the component polymers. Now, let us have a look into this effect of miscibility, immiscibility of blend composition on the properties of that polymer blend. Now, here this is the composition axis, this is the properties axis. Okay. Now, here this axis, this axis can be for a pure component polymer, say component polymer, component A, component B. Now, this is 100% over here, this is 0, here it is 0, here it is 100. So, this is the properties axis of pure B, this is the properties axis of pure A. When we mix say 10% of B with 80% of A, similarly 30% of B with 70% of A, 60%, 40% of B with 60% of A, 50, 50, 50, and gradually decreasing the amount of A from here to this axis and increasing the amount of B from here to this axis, and we will have a full range of compositions, and we can make infinite number of blends of A and B taking intermediate compositions, and one can evaluate the properties of those different compositions. Properties I mean that can be physical properties, that can be chemical properties, that can be mechanical properties, that can be thermal properties, that can be optical properties, that can be electrical properties, etc. so and so. Okay. So, in general these properties can change. Suppose this is, here lies the properties of A and here lies the properties of B. So, if we add these 2 points, we will get an additive line. That means, if we gradually mix A with B or B with A, so property changes like this. That means, if we have more proportion of A, less proportion of B, then we can have a property over here. That means, it is above this line. So, this is known as this is actually additive line, additive behavior. Okay. Then we can have a synergistic behavior like this. That means, there can be some composition, say here it is. So, here it is, suppose say 65-35 for example, 65-35. So, 65-35 composition can give maximum properties, which is neither available from this A nor B. So, that is a kind of synergistic behavior. That these are the benefit of such polymer blends having intermediate compositions, which is neither available with A nor available with B. There can be another situation where these properties line remain below the additive line. That is this system may not be useful, whereas this can be useful or this can be useful at certain composition. At any composition this is also useful. So, we can remain at any point where you like or any point where in the additive case we can remain. So, this way we can get improved properties by blending of the component polymers A and B, and we can critically analyze in between for these critically analyze these intermediate compositions about their miscibility and immiscibility. We can have several situations of miscibility and immiscibility or semi miscibility or semi immiscibility beyond this additive or in between this synergistic and additive behavior, and immiscibility will come below this additive line. So, we shall discuss in the next lecture other parts in the next lecture. Thank you.